Majumdar, and the talk is on the mathematics of liquid crystal. Please.
So firstly, I'd like to thank Paul and Andre for the invitation. So it's a pleasure to be here. So I'm Apala Majumdar from the University of Bath, and as you can tell from my title, I mainly work on the mathematics of materials science. It's really the mathematics of liquid crystals. I'll tell you what they are or what you need to know for the purposes of this talk. But in terms of what I really do, I use a combination of theory, analysis, simulations, and modeling to somehow address problems that arise in an interdisciplinary framework, also often problems that arise from industrial applications. So I should point out that my talk is very non-technical, and I deliberately kept it so because I wanted the talk to be accessible to a broad audience. And I also have a fairly long introduction, but if you don't know much about liquid crystals, it'll probably be interesting. But anyhow, I thought I'd start off by telling you a bit about myself, but in the interests of time, I'll skip the slide. Now, moving straight on to what liquid crystals are, because this is largely a non-liquid crystal audience, or at least that's my understanding. Liquid crystals, as the name suggests, are materials that are somewhere in between liquids and solids. I would say that's fairly intuitive from the name. And here I have a picture, a schematic picture of the phase transition between solids and liquids, which is sort of induced by gradually decreasing the temperature. So if you take an isotropic liquid and you slowly decrease the temperature to sort of solidify to get a crystalline solid, in some cases you will encounter intermediate liquid crystalline phases, which are the phases on the right. And I think that's probably fairly intuitive from the name. Now, liquid crystals were actually discovered by accident, and I still find the story quite interesting. So this was way back in 1888 by an Austrian biochemist. So I think he was heating a solid sample of cholesterol, and whilst he was heating it, he sort of encountered an intermediate hazy liquid, which was kind of turbid with very unusual optical properties. And that was consequently discovered to be the first experimental observation of a cholesterol liquid crystal. So I quite like that story. Now, as you might guess, there are many different kinds of liquid crystals, but I really like to work with the simplest kind. I keep things as simple as possible. So I work with pneumatic liquid crystals. They are the simplest, but also the most widely used. And in terms of what you need to understand from the point of view of this talk, is the one sentence that you need to remember to understand the rest is that pneumatics are complex anisotropic liquids. So these are liquids with directions, liquids with certain preferred directions. If you want a bit more, then the constituent molecules are typically elongated or rod-like, maybe like cylinders, short cylinders. But these molecules, these rod-like molecules, they flow about freely, as in a normal conventional liquid. But while flowing, they tend to line up along certain locally preferred directions, which is why these are liquids with a certain degree of long-range orientational ordering, or liquids with certain preferred directions. But what's interesting is that this concept of long-range orientational order or partially ordered liquid crystalline behavior is fairly, it's almost, you find it at all sort of length scales. You find it in biological systems, even human DNA. You find it in slightly larger systems, say elastomers, polymers, colloids, colloidal suspensions. And last but not the least, they are the working material of choice for the multi-billion-dollar liquid crystal display industry. The laptops, the wristwatches, calculators. So at this point, you could ask the question, what makes pneumatic liquid crystals so interesting? And the answer really just lies in that one sentence, complex anisotropic liquids or liquids with certain special directions. Now, the fact that these pneumatic liquid crystals have special directions, this necessarily implies that they respond differently to light, electric, or magnetic fields, even temperature, differently. They have different responses in different directions. And because they have different responses in different directions, they also have a very strong coupling. They couple very strongly to light and to external electric and magnetic fields. And because they have this very strong coupling, if you are an experimentalist or a practically minded person, one can use this coupling quite efficiently to actually control their physical, their electromagnetic, and their optical properties to get the desired outcome, and therefore this lends them very naturally to be the working material of choice for many portable electro-optic applications. Now, I thought I'd tell you a bit about my research program. I will say a few sentences here because I want everybody, because the talk is quite specific, but in terms of what I do, it's broader than that. So my research program, in my opinion, has three parallel but closely interlinked themes. The first theme is really just a rigorous analysis of the mathematical theories for nematic liquid crystals in a macroscopic continuum framework. So mathematically, then the tools that I use are really calculus of variations, nonlinear partial differential equations, dynamical systems, bifurcations, sort of generic applied mathematics, and looking at the analogies between the theories for nematic liquid crystals, which are really partially ordered materials, with other variational theories in materials science. So a lot of my recent work has looked at the connections between Ginzburg-Landau theory for superconductivity, which some of you may have heard of because it's more well known in the literature, with the Ginzburg-Landau theory and the Landau Dgn theory for nematic liquid crystals. And I've also invested a fair bit of time and effort in looking at defects and singularities from a mathematical perspective in confined nematic systems. And again, these are hard mathematical problems because you're really looking at systems of nonlinear, highly coupled PDEs. But this work is theoretical and can be, applications and theory is kind of separate. Now, the next question is quite generic in nature again. So nematics, like most complex materials, you can mathematically model them on different scales. That's probably clear. You have the fully macroscopic continuum level of modeling, which is where calculus of variations comes in a variational perspective. But you also have more microscopic molecular level descriptions. You have lattice-based models, you have off-lattice-based models. And what is not clear is how do we rigorously mathematically justify a passage between the different levels of modeling. And that's a pretty challenging and very non-trivial question. And last but not the least, I do spend a fair bit of time just modeling liquid crystal applications which arise in industry. So I started off my PhD being a case student with Hewlett-Packard, and I also model experiments with chemists and physicists. And this talk is really about modeling liquid crystal devices in industry because I thought that would be perhaps most suitable for a broad audience. Talk about a real application or a real experiment and see what you can say about it mathematically. Now, given that this talk is about modeling liquid crystal displays or new generations of displays, I thought I'd spend a couple of slides just telling you what the working principle of an LCD is. So nematics, they have two key properties that make them the working material of choice for these range of device applications. First, they're very sensitive to light. They're optically birefringent. They have at least two different refractive indices. And secondly, they're very sensitive to external electric or magnetic fields. These are the two key properties. So here I have a picture of the twisted nematic device. So this was one of the first LCDs to be on the market. And as you can see from the picture, the basic construction is fairly straightforward. It's not my picture. It's a picture lifted off the web. It's very easily available. I mean, almost everybody uses this picture. It's like a warm-up exercise. So what they do, the construction is straightforward. You just take a layer of nematic liquid crystalline material between two solid surfaces, really simple. And the two surfaces, they are treated. They're rubbed so as to induce a specific orientation for the nematic molecules which are in contact with the surfaces. So you somehow want to fix the molecular orientation on the two bounding surfaces. And you can think of this as being a Dirichlet boundary value problem. But the two preferred orientations for the molecules on these two surfaces, they're at right angles to one another. So informally speaking, what happens is that in the absence of an electric field, the molecules, they twist uniformly between the two preferred orientations. So you have a nice twisted configuration, which is the picture on the left, and this nice twisted molecular configuration is transparent to incident light. But then when you apply an electric field, the molecules, they like to line up with the field. So you have a more aligned configuration, which is the picture on the right, but this sort of more vertical profile is opaque to incident light. It doesn't allow light to pass through. And you actually need this optical contrast for any viable LCD. You need a bright state, a state which is transparent, and you need an opaque state, a state which is dark, and you need to be able to switch between the two states. So what's the limitation here? So it sounds all right. The limitation is that once you remove the electric field, the molecules will spontaneously relax back into the twisted transparent state. So the point is that you will need, or we, the manufacturers, they will need a constant source of power to maintain the bright and the dark states simultaneously. And this is expensive for them. So this is how my research started. We started looking at modeling bistable LCDs. And the basic working principle of a bistable LCD is that both the bright and the dark states ought to be stable without an external electric field. So you don't really need power to switch between the different states. You only need power so you don't need power to switch between the different states. I think that's the main point. And in fact, the idea is that in principle, you could maintain an image, a static image with zero power consumption, and therefore these are very lucrative from an industrial point of view. So you save power. You save power whilst you're just maintaining an image. You only need power to refresh your screen. Now, some of this is a reality. It, of course, hasn't been as successful as they had hoped it would be, but there was some success. The first example I will describe at length, which is the planar bistable liquid crystal device, and the basic construction was that they effectively had a periodic array of three-dimensional square or rectangular wells, again a very simple geometry filled with pneumatic liquid crystals. The second one has been a commercial success, at least in the UK, the zenithally bistable pneumatic device. So again, if you look at the picture, it's not such a hard geometry. You just have a layer of liquid crystalline material between two surfaces. The top surface is nice and flat, but on the bottom surface, you have this complex, relatively complex, sinusoidal grating, and this relatively complex surface morphology actually induces the bistability. So they actually do successfully get two different stable states without an electric field. That's the crucial bit. And the third one is something that I actually worked on as a graduate student. This was the post-aligned bistable pneumatic device designed by Hewlett-Packard Laboratories. It's a 3D device. That was really the main point for them. But again, the construction is fairly straightforward. A layer of liquid crystalline material between two surfaces, but the bottom surface has an array of periodic three-dimensional posts sticking out. So you effectively have a bottom surface with nice posts sticking out, a nice regular array of posts sticking out, and the liquid crystal material is actually outside the posts. But it again turned out to be bistable. So for the rest of the talk, I'll just focus on the planar bistable pneumatic device and what we can say about it mathematically. So the geometry, like I've already said, is fairly straightforward. You just have a periodic array of three-dimensional square or rectangular wells filled with pneumatic liquid crystals. From a modeling point of view, it's important to note that these are shallow wells. So the height of the well is small, less than a third of the cross-sectional dimensions usually. These were some typical dimensions, but it's usually less than a third, in some cases more like a fifth. And then the third point is the choice of the boundary conditions. That's usually very important for any liquid crystalline problem, the choice of the boundary conditions. So you have a well. A well will typically have 6 surfaces, a top and a bottom, and 4 lateral surfaces. And then the question is, what is the choice of the boundary condition? And to the best of our understanding, these are tangential or planar boundary conditions, which just means that on the well surfaces, the surfaces are treated so that the pneumatic molecules on the surfaces are actually in the plane of the surface. That's what planar would mean. So on the surface, the molecules want to be in the plane of the surface. If you look at it a bit more, what does it actually mean? Say, let's just look down at the bottom cross-section, which is roughly a square or a rectangle. What do the tangent boundary conditions actually mean? They mean that the pneumatic molecules have to be in the plane of the square or the rectangle, but therefore necessarily on the edges, they are constrained to be tangent to the edges. So for example, on the horizontal edges, they would be horizontal. On the vertical edges, they would be vertical. But then there's a problem, right? There's a very natural mismatch at the corners, and that's where you expect to see some singularities or something which is exciting, both theoretically and practically. But what was interesting from their point of view, so I should have said at the start that this device was first reported experimentally in a 2007 paper. But what was interesting at the time was that this very simple geometry, at least from their point of view, was experimentally found to be bistable. It's actually known to be multistable now. But at the time, they found at least 2 different stable states without an external electric field. The first one is what they call the diagonal state. So here, the pneumatic molecules, they just roughly align along one of the square diagonals. That's pretty much consistent with the name of the state. And the second one is where the molecules, they would roughly rotate by 180 degrees between a pair of opposite edges. So there is an interior rotation of 180 degrees, which is why they called it the rotated state. And there are clearly 4 different rotated states related by a 90-degree rotation. But for them, the main point was that both of these states are stable without an external electric field. They have long-term stability. And they also look a bit different when they looked at the optical textures with a microscope. And then for them, this was now a bistable device. So we revisited this problem with a graduate student, Alexander Lewis, who has now passed his viva, so that's very good. And we said, what can we actually do? What can we mathematically say about this device? We're not the first set of people to look at this device, but we adopted a very simple approach. So there are at least 3 different continuum theories for nematic liquid crystals. We started to work with the simplest one, the Ose-Frank theory. The Ose-Frank theory is really the simplest continuum theory for nematic liquid crystals, because it assumes that the molecules, they have a single distinguished direction of molecular alignment, and it effectively describes the entire nematic phase by a unit vector, just one vector which represents the physically preferred direction of molecular alignment. So your entire order parameters, you're just looking at one vector. And further, we restricted ourselves to 2 dimensions. So we said that because these are shallow wells, we're only going to model at what happens on the bottom square cross-section, and we're going to neglect any variations in the z direction. So at the end of the day, our mathematical object is a 2-dimensional unit vector field n. And if you have a 2D vector field n, you can parameterize it completely by an angle theta. The next thing we did, because ultimately we're interested in looking at the diagonal and the rotated states, so we prescribed some boundary conditions, which we effectively prescribed 3 different boundary value problems, which are consistent with the experimentally imposed tangent boundary conditions, and which also somehow mimic the diagonal and the rotated states. So we ended up with 3 different boundary value problems. Now, the Ose-Frank theory is a variational theory. And those of you who do calculus of variations will know that these theories, there's usually an associated energy functional. And the hypothesis usually is that we want to compute minimizers, global or local, minimizers of these energy functionals subject to the imposed boundary conditions, and the expectation is that these minimizers, these energy minimizers, will model the experimentally observed physical equilibria. So that's what we did, but we made it even simpler. We worked with the simplest possible form of the Ose-Frank energy, which is really just the Dirichlet energy, and then the mathematical problem reduces to solving the Laplace's equation on a square, which is not, you're solving the Laplace's equation on a square with Dirichlet boundary conditions. So at this point, you could ask, well, what's challenging? Well, there is a challenge, actually. I mean, it's not perhaps, it is technically difficult for a reason. It's because you have those point defects at the corners, and the Ose-Frank energy actually blows up at the corners. That's a calculation you can do. And that makes this technically non-trivial, even though perhaps conceptually or clear, but technically non-trivial. And the asymptotics are not, it's a fair bit of work, because what we have to do is we have to look at an x-sized rectangle. So now we've gone from a square to a rectangle because these methods are fairly general, and you have a rectangular aspect ratio lambda. And what we could do, using, I would say, non-trivial asymptotics, is compute fairly explicit estimates for the Ose-Frank energy on these x-sized rectangular domains in terms of the rectangular aspect ratio lambda. And this gives us fairly explicit information, and once you compare these estimates, what you can see straight away is that the diagonal state always has lesser energy than the rotated solutions, which is also consistent with experiments, and you can actually do more. You can explicitly estimate some experimentally relevant variables like the surface extrapolation length. I don't have a lot of time left, but the second half of my talk is actually looking at a far more sophisticated theory, which is the Landau Dgn theory. It's one of the most powerful continuum theories for nematic liquid crystals in the literature. Maybe I should hurry up. But the main point here is now that you have a far more complex order parameter. The Landau Dgn theory, it describes the nematic phase by a symmetric, traceless 3x3 matrix. So you straight away have 5 degrees of freedom, which somehow contain information about both the directions of preferred alignment and also the degree of ordering about these preferred directions, which was actually absent in the Ose-Frank theory. You can describe a great deal more. So it's a symmetric traceless 3 by 3 matrix. You can use the spectral decomposition theorem. You can actually have a classification in terms of the eigenvalues, but I'll just point out the two important things that you do need to understand. The first case is the uniaxial case, where the Q tensor will have a pair of degenerate non-zero eigenvalues, which effectively means that the Q tensor has a single distinguished direction. That comes from the name. Uniaxial means one single distinguished direction of molecular alignment. And the more generic case is the biaxial case, where you actually have three distinct eigenvalues, and you have a primary and a secondary direction of molecular alignment. So it's a variational theory. So you have the same sort of ideas again. You have a fairly complicated energy functional. If you look at the energy density, you will see that there are two separate contributions. There's the bulk potential FB, which is a non-convex degree 4 polynomial in the eigenvalues. And the idea is, because we don't really have time, the idea is that it somehow dictates the preferred phase of the nematic material, whether it wants to be uniaxial, biaxial, or isotropic. I think that's all you need to know, as a function of the temperature. The second component is the elastic energy density, and this is fairly intuitive. This will penalize any spatial inhomogeneities in the system. And in terms of what we do mathematically, we look at the corresponding Euler-Lagrange equations, which are a nonlinear system of 5 coupled elliptic PDEs. And this is why this is a hard mathematical problem. Now, what did I actually do? Or what did we actually do? So this is all joint work with various different people all over the place. So we started off, so we said we've looked at a square, so now let's look at the full 3D box. Let's look at a fully three-dimensional box, because the real device is three-dimensional. On the lateral surfaces, we imposed Dirichlet conditions, which means we effectively fixed the Q tensor. That's what Dirichlet means. You just fix the Q tensor on the lateral surfaces consistently with the experimental tangent boundary conditions, but on the top and the bottom, we kept it free. And that's consistent, again, with the tangent boundary conditions, because we want to allow the nematic molecules some freedom on the top and the bottom, because they can actually point in any direction within the plane. So we have to give them that freedom. And then a lot of this work is numerical. For using finite element methods, you can minimize the Landau Dgn energy on these 3D boxes once you have agreed on how to implement the tangent boundary conditions. So we did that. And for fairly large boxes, when I say large, I mean on the micron scale, because remember, nematic molecules are nanometers. They're 10 to 20 nanometers, so large would be microns, right? 30 to 60 microns is large. We did that, but we didn't really get anything exciting. We just recovered the diagonal and the rotated states, and you get all the 6 states again. And that wasn't terribly rewarding, so we decided to make the boxes smaller and see if we get something new. Now, when you say smaller, you need to make the concept of large and small precise. So at this point, we started measuring length in units of a typical material-dependent length scale called the biaxial correlation length. I'll spare you the details, but it's a material-dependent length scale, and we started measuring length in units of xi. So it's a material-dependent length scale. And we started to talk about biaxiality, because biaxiality is something that is not captured by the Ose-Frank theory at all. You cannot understand biaxiality with Ose-Frank theory, because Ose-Frank theory is based on the premise that there's only a single direction, so it's effectively restricted to uniaxial materials. We started talking about biaxiality. It's a definition accepted in the literature. What you need to know is that if beta squared is equal to 0, that it means that the phase is almost uniaxial, and if beta squared is equal to 1, that means it's maximally biaxial, which means that the Q tensor has a 0 eigenvalue, but I think maximally biaxial is good enough. Now, if you look at the square here, this is for one of the large boxes. And if you look at the profile of beta squared, you will see that it is dark almost everywhere. What's that telling you? The dark means beta squared is almost 0. This is telling you that the profile is almost uniaxial everywhere, but you have these bright lobes, these bright regions right near the corners where you have defects. So the only conclusion is that the diagonal and the rotated states are predominantly uniaxial, and you only get biaxiality heavily localized near the vertices. And if it is predominantly uniaxial, then the Ose-Frank theory is probably good enough. But then what happens as you start to make the wells smaller? If you keep looking, then you will see that the bright lobes, they're becoming larger relative to the domain size. They start to overlap, and then there's a critical well size, which is the top right picture, where you get this connection. And that's the new well-ordered reconstruction solution, which was not previously reported in the literature. This is very interesting. It's a shame that I left it to the last minute, but this was the novelty. This wasn't reported in the literature, and it wasn't obvious at all. And just a few words about the profile. It is uniaxial near the edges, and that's because we've imposed the Dirichlet conditions. Then it's also uniaxial along the square diagonals. It's actually uniaxial. You actually have a defect. Without going into the details, there's actually a very pronounced defect line connecting the 4 square vertices along the 2 diagonals. And this defect line is surrounded by that bright star-shaped rim of maximal biaxiality. And what you have is a very nice pattern, uniaxial on the edges, then you have the biaxial star-shaped rim, and then you have it being uniaxial on the diagonals again. So it's uniaxial, maximally biaxial, and uniaxial again along the diagonals. And this is new. This wasn't reported in the literature. I'll skip most of this, but I will show you the bifurcation diagram as a function of the square size. I think that's very good numerics, even if I am a co-author. But I was a lot of the numerical work has been done by Martin Robinson. Some of this using techniques by Patrick Farrell and previous work done by Xiong Liu. And then Radek and I were putting an input in other directions. But if you look on the extreme left, you will see a unique solution branch, the green branch, if you can see it. The green branch is the well-ordered reconstruction solution, which was not previously reported in the literature prior to our work. And then you see, as the well size becomes larger, you get more branches. And finally, for very large well sizes, if you start to look at the right, you will see 6 different branches, which are the conventional diagonal, the 2 diagonal solutions, and the 4 rotated solutions. So the take-home message is that the O-Saint-Frank theory, which is the simplest possible theory, did capture the right-hand side of the spectrum, but as you would expect, did not capture the left-hand side of the spectrum, especially the new well-ordered reconstruction solution. And my last slide is the fact that we actually computed 21 different states, of which, of course, only the diagonal and the rotated are stable for large well sizes, and only the well-ordered reconstruction is stable for small well sizes. But you do have these multiple critical points, 21 different critical points, which are actually featured by reasonably stable interior point defects. So we thought that was interesting, and the work will hopefully be accepted very soon. I'd like to thank my funding bodies, and I'd like to thank you for your attention.